In previous lecture, I discussed what is bipartite graph and matching. In case of bipartite graph, we divided the set of vertices into two groups like B1 and B2, and there can be edges from B1 to B2, but there cannot be edges in between B1 or in between B2. So that is a bipartite graph. For example, suppose this is B1, this is B2, and there are some vertices like this. So there can be edges from B1 to B2 and from B2 to B1, but there cannot be edges between B1 or between B2. And matching is a subset of set E of edges such that no two edges are adjacent to each other. For example, this is a graph and there are some matching of it. Here M1, M2, M3 and M4 are matching of it. If a vertex having degree 1, then it is matched. If a vertex having degree 0, then it is not matched. So here C and A are not matched. Here A and B are not matched. And here M1, M2 and M3 are matching where we cannot add any more edges. Like here, if we'll add any more edges, then that will be no more matching. But in case of M4, we can add a edge. Here matching number is 2. In case of maximum matching like M1 and M2, there are 2 edges. So matching number is 2. And what is complete matching? In case of bipartite graph, if every vertex of B1 are matched, then that is a complete matching. And for complete matching, B1 length means number of vertices in B1 should be less than or equals to number of vertices in B2. This is an example. This is a maximal matching but not complete matching. So here number of vertices in B1 are more than number of vertices in B2. Here 3 vertices, whereas in B2 there are 2 vertices. So 1 vertex is left, but in case of complete matching, every vertex of B1 should be matched. So that's why it's not a complete matching, but it's a maximum matching. Next, theorem 6, that is Hall's marriage theorem. The bipartite graph G equals to BE with bipartition B1 and B2 has a complete matching from B1 to B2 if and only if n of A is greater than equals to A. Means number of vertices in neighborhood of A is greater than equals to number of vertices in A for all subset A of B1. So let's take an example. Suppose this is B1 and B2. B1 have vertices like A, B, C. It have 3 vertices, and B2 have vertices like 1, 2, 3, 4. It have 4 vertices. And now there are some edges like this. I'm just considering randomly. Now, is complete matching possible for this B1 and B2? Here A, B, C. Here 1, 2, 3, 4. Now, I'm considering A to 1, B to 4, then C to 2 or 3. So, complete matching possible. Let's take a subset A of B1. I'm just considering these two. We can take any subset. We can take just AB, BC or ABC or single A, B, C. There can be any subset. Now, neighborhood of A. So, neighborhood of A contain A neighborhood are 1 and 2. B neighborhood are 1 and 4. So, we got 1 to 4. Here, length is 3 where length of A is 2. So neighborhood of A, 3 is greater than 2. Let's take another example. Let A contain B, C. So length of A equals to 2. Number of vertices in A equals to 2. B neighbor are 1 and 4. C neighbor are 2 and 3. So it is 4. So obviously 4 is greater than 2. Hence neighborhood of A is greater than or equals to A. So in short, it is saying number of vertices in B1 should be less than equals to number of vertices in B2 such that complete matching is possible. So number of vertices in neighborhood of A should be greater than or equals to number of vertices in A, and A is a subset of B1. I think you guys are clear in Hall's marriage theorem. that number of vertices in neighborhood of A should be greater than equals to number of vertices in A, and A is a subset of V1. Let's take an example. Example 13. For which of the following graph complete matching exists? And I consider 5 graph. Now I will check for this 5 graph complete matching is possible or not. Now first option, here in V1 contain 1, 2, 3, 4 vertices, whereas V2 contain 3 vertices. Number of vertices in V1 is greater than number of vertices in V2. That's why complete matching is not possible. For complete matching, length of V1 should be less than equals to length of V2. But here it's greater than. That's why for option A, complete matching is not possible. Now check option B. V1 contain 4 vertices, V2 contain 4 vertices. So both contain equal number of vertices. That means complete matching possible. Let's check the edges. So here this we can consider. Now for this vertex we can consider this. Then for this vertex there are no adjacent. If we use this one, then it will be no more matching. So 2 edges will be adjacent. And for last vertex we can consider this. So no complete matching possible as 2 vertices are adjacent to 1 vertices of V2. That's why complete matching doesn't exist. Next check option C. Here also V1 contain 4 vertices, V2 contain 4 vertices, equal number of vertices, so complete matching possible. Let me take some name like A, B, C, D. Here also 1, 2, 3, 4. Now for matching I will consider A1, B2, C3. Now for D is adjacent to 3. Already I considered C3, so I cannot use this edge as both edge will be adjacent. So complete matching doesn't possible as C and D both are adjacent to 3. Next option D. Here V1 contain 4 vertices, V2 contain 1, 2, 3, 4, 5 vertices. Complete matching possible. Now let's consider this. Then here this. Yeah. Complete matching possible. All vertex of V1 are matched, so complete matching possible. Next check option E. Here V1 contain 4 vertices, V2 contain 4 vertices. Let this for B, I'm using this one. For next, let's this. For last this. Yeah. Complete matching possible. For option A, complete matching is not possible as number of vertices in V1 is greater than number of vertices in V2. For B and C, complete matching is not possible as there 2 vertices of V1 are adjacent to 1 vertex of V2. Next definition 8, it's about subgraph. A subgraph of a graph G equals to V is a graph H equals to WF, where W is subset of V and F is subset of E. A subgraph H of G is proper subgraph of G if H not equals to G. Let this is a graph having 4 vertex A, B, C, D. Then we can say A, B, C is a subgraph of this. It is a proper subgraph as H is not equals to G. Okay, as both are not equal. Next, union of 2 graph. The union of 2 simple graph G1 equals to B1 E1, G2 equals to B2 E2 is a simple graph with vertex set B1 union B2 and A set E1 union E2. So the union of G1 and G2 can be done by G1 union G2. Let's take an example that you can understand. This is G1, G2, AB, here also AB. So in G1 union G2 there will be edge from A to B. Now here A to D, here no edge. So in union we'll add edge from A to D. B to C, here B to C, B to C, then B to E, here no edge. So we'll add a vertex E and there will be edge from B to E. Now D to E, there will be D to E, then D to B. So here D to B. So we'll combine all the edges of G1 and G2 and that will be in G1 union G2. Next, some application of special type of graph. We can use special graph in LAN. I already discussed some special graph like cycle graph, wheel graph, ring graph, complete graph, bipartite graph. So first LAN technology is star topology, where all devices are connected to the central device. So that we can represent as K1N. K1N. It's a bipartite graph. There will be one vertex in one group and n vertex in another group. So a local area network can be represented using complete bipartite graph K1N as shown in the figure A. This is our figure A, K1N. Here it is 1, 2, 3, 4, 5, 6, 7, 8. So you can say K18. There is one central vertex and there are 8 sides. So every communication are through this central node. Next is ring topology, where we use a cycle. So here each device are connected to exactly two other. One is left vertex, another is right vertex. So local area network with ring topology are modeled with n cycle, where each vertex are adjacent with its left vertex and its right vertex. So ring topology use the cycle graph, whereas star topology use the bipartite graph, and some LAN uses the hybrid of these two topology, like it is a ring, also it is a star. So that uses the wheel graph. Okay, if in a cycle we are adding a center vertex and there are edges from that central vertex to every vertex, that is a wheel. So wheel graph we can use for a hybrid topology. There are multiple uses of graph. This is just some sample. Like in LAN we can use, in mathematics, in TOC, in DBMS, in algorithm, in every subject we are using graph. Graph is the basic. Okay. With this I am finishing first topic of graph theory. Here I discuss type of graph, type of edges, complete graph, bipartite graph and matching. In next lecture I will discuss graph representation and isomorphism. If this lecture is helpful for you, please like, share and subscribe. Thank you.